Hello everyone, today we will be exploring Boolean algebra, a fundamental concept in digital logic design and computer science. Boolean algebra helps us simplify logical expressions and design efficient digital circuits. Boolean algebra uses variables that only hold binary values to represent 1 or 0, true or false, on or off, and yes or no. In today's topic, we will learn two methods to simplify Boolean expressions, which are algebraic method and Karnaugh methods, and also how to draw a logic circuit. First, to use the algebraic method, we will have to know some basic rules and theorems. The first rule is identity laws. The identity element in Boolean algebra states that adding 0 to any variable a gives a itself. Similarly, multiplying 1 with any variable a also gives a. These are fundamental properties that help us simplify expressions. The second law is the idempotent laws. These laws state that if a variable is or ANDed with itself, the result is still the same variable. This means no need to write the same variable twice in an expression. Third, complement laws. The complement laws help us understand how a variable interacts with its negation. This means a variable or with its negation is always 1 and ANDed with its negation is always 0. Fourth, involution law. This law states that if you take the complement of a complement, you get back the original variable. This tells us that applying not twice brings us back to the original state. Fifth, the commutative laws state that the order of variable doesn't matter in and or operations. This is similar to basic arithmetic where 2 plus 3 equals to 3 plus 2. 6. The associative laws allow us to group variables differently without changing the result. This helps when simplifying complex Boolean expressions. Last but not least, let's take a look on the distributive laws. Just like in regular algebra, Boolean algebra follows the distributive property. This is useful when expanding or factoring expressions. Now is the theorem part. So, first is the minimization theorem. This means that if we have a variable and its complement both ANDed with another variable, the result is simply that variable. This shows how using both a variable and its complement within an OR operation can simplify the equation to just be. Second theorem, which is adsorption theorem. This means that if a variable is OR with its ANDed form, the result remains the variable itself. This is because A already covers the case where ABC is true. Here, if A is ANDed with the OR operation of itself and another variable, the result remains A. Third theorem, which is simplification theorem. This simplifies the equation by eliminating redundancy. This theorem helps simplify expression by using the property of complements. So the last theorem, which is the De Morgan theorem. The first theorem shows that the complement of an AND operation is equivalent to the OR of the complements. Second theorem shows that the complement of an OR operation is equivalent to the AND of the complements. So now let's apply the basic concept into our past year questions. We are given two Boolean expressions, f and g. Prove that f equals to g use Boolean algebra rules and identities. We start with bar a and b and a plus c, or bar a and b, or bar b and bar c. So we expand the expression using the distributive concept. So it will become complement a and b, or complement a and b and c, or complement a and b, or complement b or complement c. And then we apply the idempotent rules because complement a and b appears twice. Next, we apply the complement rules. So it becomes complement a and b and c, or complement b or complement c. This is because complement a and a equals to 0 according to the complement rules. The next steps we simplify. So it becomes complement a and b, or complement b or complement c. And then we do further simplifications by complement a and b or complement b. So we get the final answer is the complement a or complement b or complement c. Now, let's see the second part of our topic, the Karnaugh map. We call it as K-map. Provides a visual way to minimize logical expressions by grouping adjacent ones in a grid presentations. So these are the rules to draw a Karnaugh map. First, cells with 0 cannot be part of any group. The objective is to cover all the ones in the grid efficiently. Second, each group must contain 1, 2, 4, 8 or more cells in powers of 2. Third, to achieve the most simplified expression, groups should be maximized. If a larger group can be formed without violating the rules, it should be prioritized. Fourth, a single one can be part of multiple groups. This redundancy helps further simplification by covering terms efficiently. Fifth, since the K-map is cyclic in nature, the leftmost and rightmost columns are adjacent, just like the top and bottom rows. This means ones appearing on the edge can be grouped together. Similarly, corner ones can form a valid group. Last rules. The goal is to use as few groups as possible to simplify the expression. Fewer groups result in a simpler Boolean equation. Move on, we will use another alternative to prove this Boolean expression. First, we need to have a truth table. Identify variables from the original Boolean expression to know how many columns we have. The number of rows required depends on the number of positive literals. Fill in the binary value 1 or 0 into the table to get the truth value. Then we create a K-map grid. Number of cells based on 2 powers of number of variables. So in this case, the number of cells is 8 since there are 3 variables, which is 2 power of 3. Write down the variables at the top right corner. Label each cell and take note, last 2 column orders are 11 and 10 instead of 10 and 11. Now we need to fill in 1 into the grid based on the truth table. If the truth table value is 1, fill in 1 in the corresponding grid, otherwise it is 0. In this case, only a truth assignment gets 0, so to make it easier, we fill in 0 into the corresponding grid, which is 1, 1, 1, else we fill in 1. Now we need to group up those 1 with the rules we just learned. Obviously, the largest is this. We group as more 1 in a group as we can. And don't leave out the left bottom corner 1, we can group it with the top right corner 1 even though it is overlapping. As a result, we have 3 groups, and we need to find the common factor within the groups. So we get the answer, which is complement A or complement B or complement C, same as expression G. The last part of our topic, logic circuits symbols. So the NOT gate, it inverts the input, meaning if the input is 1, the output is 0, and vice versa. AND gate, the output is 1 only if both inputs are 1, otherwise the output is 0. NOT AND gate, the inverse of AND. OR gate, the output is 1 if at least one input is 1. The output is 0 only if both inputs are 0. The NOT OR gate, it is the inverse of OR. Exclusive OR gate, if both inputs are the same, the output is 0. Last question, we will draw a logic circuit based on the original expression. Let's identify the gates we need and the inputs, and separate expressions into a few parts. To make it easier, I separate complement A and B as part 1, A or C as part 2, complement A and B and A as part 3, complement B and complement C as part 4. First part, draw the complement A and B with the NOT and AND gate. Second part, connect A and C with the OR gate. Then connect first and second part with the AND gate. After that, we're going to build out our last 2 parts. Third part, repeat steps in first part and connect with another A input using AND gate. Fourth part, draw the complement B and complement C using the NOT gate and connect them with OR gate. Connect the third and fourth part using OR gate. Move on, connect the first half and the last half parts together using the OR gate. Lastly, verify correctness once again, step by step. Thus, the logic circuit is done. As a recap, let me summarize the key points of today's video. How to simplify when proving a Boolean algebra expression using algebraic method. Write the given Boolean expression clearly, apply Boolean identities, eliminate redundant terms to simplify the expression, verify it further simplification is possible. Express the result in its simplest form. As for the alternative, which is the K-map method, determine the number of variables, create the K-map grid, fill in the K-map, group the ones in largest possible power of 2 groups, write simplified Boolean expressions from the groups. How to draw logic circuits. Identify the simplified Boolean expression from K-map or algebraic proof. Select logic gates based on the expression. Arrange logic gates in a circuit diagram to match the expression. Verify correctness by comparing truth tables or simulating. That's all for today. Thank you and happy learning!